that is, tumors with Gleason score 4+4, are in fact highly aggressive carcinomas with poor prognosis. Since there is no special separate treatment for so-called intermediate aggressive carcinomas, they should be classified since the very beginning as high aggressive malignancies. Results of a study of more than 200 prostate carcinomas showed that the global spatial capacity fractal dimension D0 and the global spatial information fractal dimension D1 were the best classifiers. The entire set was divided into 7 classes of equivalence according to the values of those two dimensions. See scatter plot A and B. The other complexity measures, such as the mean local fractal dimension, see scatter plot A, diversity measures, that is, entropy and lacunarity, see scatter plot D, didn't have a precise monotonic curves. Nonetheless, they confirmed the correctness of the stratification of the carcinomas into the appropriate classes, because their values concentrate around the mean value for each class. In addition, entropy increased along the D0 or D1 value, see scatter plot B, indicated the direction of the complexity increment in prostate carcinomas and the natural course of the disease. Data mining allowed me to find 2 quantitative criteria based on all the above-mentioned complexity and diversity measures. Those criteria define unequivocally low complexity, low aggressive and high complexity, high aggressive carcinomas. Those criteria can be applied in future clinical and pathological studies to define complexity of tumor structure in the objective manner and related to the course of disease. A study performed in cooperation with Mihai Tănase in 2015 defined a homogeneity measure. That is a novel parameter for the evaluation of tumor aggressiveness called dispersion and marked by a symbol HD. The slide A showed the principle of the homogeneity algorithm. In that algorithm, the 5 squares S0, S1, S2, S3, S4 of size L slide over the analyzed two-dimensional image of cancer cell nuclei. The algorithm calculates the parameter HD comparing a number of cell nuclei in the square S0 with the sum of the number of cell nuclei in the squares S1, S2, S3 and S4. The slide B shows the idealized evolution of the local structure correlation diagram along the evolution of carcinoma structure. This comprises the evolution from the homogeneous structure of normal prostatic tissue, marked on the diagram 1 as A, to the other homogeneous structure such as cancer cell infiltration, marked as B on the diagram 5. The diagrams 2, 3 and 4 show the intermediate stages of heterogeneous structures corresponding to low, intermediate or high-grade cancer. A simulation of the cellular automata mix defined a theoretical frame for a specific geometric representation of the cell nuclei distribution called the local structure correlation diagram. On the slide on the right side is shown the evolution of both the dispersion HD and the center of the cloud of points HC. As expected, the HD curve is almost symmetrical. This means that the mix of two different sets of elements operating according to different rules will be dominated by one of them eventually. In consequence, the initial spatial homogeneity of the mix of elements will be replaced by the homogeneity of a compact set of elements conquering the available space on the cost of the second kind of elements. On that slide are shown 3 local structure correlation diagrams marked by the letters D, E and F that reflect the spatial distribution of cancer cell nuclei in prostate carcinoma of the class C1, CA, class C4, CB, and class C7, CC. The appropriate numerical values of the dispersion HD for those 3 diagrams are 29, 47 and 30 respectively. It is worth to notice that the pattern representing the complexity class C4 has the areas of both cellular infiltration and glandular structure. This fact is reflected by the extended cloud on the local structure correlation diagram. See subfigure E. The clouds of points for the other 2 patterns are located in the upper right corner, see subfigure D, and in the lower left corner, see subfigure F, as predicted by the cellular automaton mix model. Subsequently, both the local structure correlation diagram and dispersion HD were computed for each of 200 carcinomas of the data bank. Data mining generated some quantitative criteria describing tumor aggressiveness. The novel homogeneity measure, HD, identifies carcinomas with very low aggressiveness within the class of complexity C1 or carcinomas with very high aggressiveness in the class C7. Alterations in tumor architecture along progression are associated with some changes in both shape and the quantitative characteristics of the local structure correlation diagram, consistent with those in the automata mix model. Low-grade prostate carcinomas with low complexity and very low biological aggressiveness are defined by the condition D0 lower than 1.545 and HD lower than 38. High-grade carcinomas with high complexity and very high biological aggressiveness are defined by the condition D0 is larger than 1.764 and HD lower than 38. Having said that, I am ready to present novel findings. Those findings appear to confirm the existence of fractal structure in the spatial distribution of cancer cell nuclei. For this part of the project, the images representing all classes of equivalence were transformed into the intensity curves. Those curves are of non-ergodic nature. For the clarity reason, I usually show the results for the carcinomas representing the class C1, C4 or C7. Please note the fact that as scanner goes along the axis X from left to the right, distance pixels play a role of the units of time. The visual recurrence analysis was performed using the software written by Eugene Kononov in 2005. The VRA algorithm detects hidden patterns across a one-dimensional series of scalar observations produced by a multidimensional system. If the underlying signal is truly random and has no structure, the distribution of colors over the recurrence plot is uniform and homogeneous. If there is some hidden order in the series, some characteristic distribution of colors can be seen in the recurrence plot, reflecting the interactions of all variables that define the dynamic system. Briefly, a one-dimensional series is expanded into a multidimensional space in which the underlying dynamic process occurs. Using a method of delayed coordinate embedding, a phase space portrait of the process will be deciphered from a single scalar series. Once the system is reconstructed, a recurrence plot can be used to show which vectors in the reconstructed space are close and far from each other. More specifically, visual recurrence analysis calculates the Euclidean distances between all pairs of vectors and codes them as colors. Essentially, the recurrence plot is a color-coded matrix where each entry is calculated as the distance between vectors in the reconstructed series. After the distances between all vectors are calculated, they are mapped to colors from the predefined color map and are displayed as colored pixels in their corresponding places. A recurrence plot is a graphical representation of a correlation integral. This figure presents results of the visual recurrence analysis in the control package of spatially distributed points. See subfigure A1, B1 and C1 in the column on the left. The random distribution of points on the surface is represented by white noise, figure A1 and A2. The distribution of points with fractal dimension represents the Hannon attractor, see subfigure B1 and B2. The highly ordered distribution of points is represented by a sinus function, subfigure C1 and C2. In the column on the right are shown results of the visual recurrence analysis in a set of cancer cell nuclei isolated electronically from prostate carcinomas, belonging to the classes of equivalence C1, C4 and C7. As can be seen in the diagrams D, E and F, in all cases of prostate carcinoma, transformation of the spatial distribution of points in the curves preserve the existence of fractal structure. It is interesting that even infiltration of the entire surface in highly aggressive prostate carcinomas is not random but has some remaining fractal structure. If a function c of epsilon is the probability that two arbitrary points in a set are closer together than epsilon. The correlation dimension is given by the ratio logarithm of c over logarithm of epsilon in the limit of epsilon approaching 0 and n approaching infinity. A non-integer value of that expression defines the correlation fractal dimension. For the random series of numerical values, such as those representing the white noise, the correlation dimension graph is a straight line. Indeed, no matter how the white noise is embedded in the space, it fills that space evenly. Chaotic or periodic series have a distinct spatial structure, and the corresponding correlation dimension attains plateau at some point as the embedding dimension increases. On the figure are shown curves with the values of the embedding correlation dimension characterizing series corresponding to the distribution of cancer cell nuclei in prostate carcinomas of class C1, C4 and C7. One can see the curves of the plots typical for the series with fractal dimension. See column 4 on the right. This table summarizes results of the visual recurrence analysis. The values are presented as a mean, median and standard deviation in each class of equivalence for prostate carcinoma as well as for benign prostatic hyperplasia. It can be seen that there is no significant difference between the values obtained for hyperplasia and carcinomas. However, the mean values increase in each class, but the classes C5 and C6. This latter finding may result from the relatively low number of cases, as well as from the fact that those prostate carcinomas possess topology similar to that in the class C4, yet still different from the class C7. Fragmentation is a ubiquitous phenomenon in nature. The fragmentation problem can be treated, among other, from the perspective of geometric statistics. Should the spatial distribution of cancer cell nuclei be random, would also be the process of fragmentation of the intensity curve random. Let us consider probabilistic fragmentation of a line, such as intensity curve, that emerges by random selection of fracture sites. Then, the process of fragmentation would be described by the Poisson probability density function, given on the slide. That Poisson distribution has the typical hyperbolic curves reflecting a relationship between the size of fragments and their frequency in the set. A comparison of both images, at the assumption that the mean density of white points is the same in both cases, leads to the conclusion that the Poisson distribution is impossible in cases with clustering of cancer cell nuclei as well as in carcinomas with preserved glandular structure. See subfigure on the left. Perhaps it is barely possible in the cases with cellular infiltration. The size-frequency algorithm takes a collection of fragments of the intensity curve of linear size x and defines as n of x the number of fragments whose linear size is greater than x. If the set is distributed according to a power law, it is a self-similar fractal, and the size frequency, called also fragmentation dimension, is defined as the exponent d in the appropriate power law equation. Indeed, the plots on the slide show consistently, even in highly aggressive carcinomas with the significant cellular infiltration, that the fragmentation of the intensity curves is described by the power law with fractal dimension. Usually, one can see in the latter cases that the slope of the fragmentation curve is much steeper than for carcinomas of the other classes. It should also be noticed that all curves are non-hyperbolic. Although the mean values of both the fragmentation dimension and the fragmentation coefficient decrease from one class to the other, but the class C7, the differences are not statistically significant. However, each intensity curve in this study was consistently characterized by the fragmentation fractal dimension. Both the mean and the median for benign prostatic hyperplasia are larger than in the case of carcinomas. Variability among hyperplasia cases is also significant, what indicate the values of standard deviation. In consequence, no statistical difference between carcinomas and benign prostatic hyperplasia was found. Finally, the